Connected particles such as this car and caravan will act as one mass, i.e. they will have the same velocity and acceleration. In this particular example, we're told that they are moving with a constant velocity, so that means that our acceleration is 0. We've been asked to find the tension, T, and the power, P, which is propelling the car forward. We're going to start with looking at to find T, and we're going to focus just on the caravan, and we're going to resolve the forces there horizontally. So what we can see is that for the caravan, forces that we've got acting on that horizontally are T minus the friction F2, and because we know that the acceleration is 0, that will equal 0 because F net equals ma and a equals 0 in this particular case. So that means our tension will be equal to F2, our friction force on the caravan. So to find our friction force on the caravan, we first need to find the reaction on the caravan, which is R2. And so resolving vertically this time, we can see that R2 will equal 2000 G, and using F equals mu r, where mu is 0.25 in this case, times our r, and we can find that F2 is going to be equal to 500 G newtons. Sometimes they're happy for you to leave it that way without multiplying by the 9.8. And if F2 is that, then T is that. So we found T. So now we're going to find P. And to do P, we're going to focus on the car this time because, of course, P isn't acting directly on the caravan. So again, if we look at the forces that are involved here, we've got P minus T and minus the friction F1. And again, because the acceleration is 0, those will total 0. So we need P, which is going to equal T plus F1. We've just worked out T, so we need F1. And we're going to get F1 in the same way that we got F2 by resolving vertically, first of all, to see that R1 equals 1000 G. And then F1 will equal 0.25 times 1000 G, so that means it will be 250 G newtons. And so our power is going to, our P force rather, is going to be 500 G newtons plus 250 G newtons. So altogether that's going to be 750 G newtons. Pulleys or pegs are always considered to be smooth, and therefore the tension either side of them will be equal, it will be the same. Here we have two particles that are held level on either side of a smooth pulley and then released. Find T when they are released. So we're going to start by looking at A. So I'm going to say that movement is most likely for A to be up and for B is going to be down in that way. So for A, we've got our F net is going to be T minus the 4G, and that will equal the mass of A, which is 4, times by the acceleration, which we don't have just yet. Okay, now we can do something similar for B. So in that case, we're going to have T minus 6G equals 6 times minus A in this example because it's going in the other direction. So although we don't know what A is, we've got two equations that have T and A in them, so we can eliminate the A and work out what the T is once we've done that. In order to do that, let's just tidy these up a little bit first of all. So we've got T minus 4G equals 4A, and T minus 6G equals minus 6A. So simultaneous equations, because we want to get rid of the A, we want to make those the same value, so we're going to turn them both into 12A. So in the first case that means multiplying by 3, so we get 3T minus 12G equals 12A. And then in the second case we're going to double everything, so we'll have 2T minus 12G equals minus 12A. So if we add those two together, then you can see that the 12A and the minus 12A will cancel each other out. So we're adding them together. We get 5T minus 24G equals nothing. And so T will be 24G divided by 5. Next, they want us to find out how far A and B move before they come to rest a half a second after release. So we know that the time is 0.5 seconds. We know that the final velocity is 0 because it's coming to rest. We want to find S. So we're going to use S equals VT minus a half AT squared, which means we need to find that acceleration. Now we had those simultaneous equations before, and that was linked to acceleration, and we worked out what T was. So T worked out to be 24G over 5. And one of the equations we had was that T minus 4G equaled 4A. So we've got 24G over 5 minus 4G equals 4A. Putting that all over 5, we get 24G minus 20G over 5 equals 4A. And so that leads us to having 4G over 5 equals 4A, and so the acceleration must be G over 5. So now we can put that information in to find out how far they've moved. So S is what we want to try and find. V is 0, so we don't need to worry about the first bit. So we want minus a half times by the acceleration, which is G over 5, times by the time squared, so that's a half squared, so that's a quarter. So altogether that's minus G over 40, and then if we work that out, that becomes 0.245 meters. Now I've kind of lost the minus because it's kind of a bit irrelevant. One of them's moving up 0.245 meters, the other one's moving down 0.245 meters. In this diagram we've got a peg resting on the end of a table here, and we've got two particles again attached across that peg. And we need to find T, the tension in the string between these two particles when they're released from rest. First of all, we can work out that R must equal 2G by resolving vertically. And so that leads us to work out that the friction will be 0.2 times 2G, which means it's going to be 0.4G. So we've got our friction there. So now we're going to resolve horizontally, taking into account that it's going to be moving. So we're going to have T minus F equals the mass of A, which is 2, times the acceleration. That's T minus 0.4 g equals 2a. Now again, we don't know what that acceleration is, so we're now going to focus on particle B. So in terms of particle B, it will have the same acceleration, and this time we've got T minus 5g, because it's got the weight acting upon it, not friction, and that will equal minus 5a, because it's in a different direction. So now again, we want to find out what T is, so we need to eliminate the A. So this time we're going to multiply this one by 5 and this one by 2 to make the A's the same. So now we've got 5t minus 2g equals 10a. Multiplying the second one by 2, we're going to get 2t minus 10g equals minus 10a, and then adding those together, we're going to get 7t minus 12g equals 0. So t equals 12g over 7, which is 16.8 newtons. Now they want us to work out how long it takes for B to come to rest if it descends 0.8 meters. So what do we know? We know that it's coming to rest, so that means that the final velocity is 0. We know that the distance it's travelling is 0.8. We want to find the time. So we've got S equals Vt minus a half AT squared. But for us to use that, we need to know what A is. We can do that by going back to those simultaneous equations we had before. So we know now that T equals 16.8 newtons, and we knew that T minus 5g equaled minus 5a. So we've got 16.8 minus 5g equals minus 5a. So a equals 16.8 minus 5g all over minus 5, which means that it equals 6.44 meters per second squared. Now we have the acceleration, we can substitute that in, but we need to be a bit careful and make sure that we're not mixing up our directions. So B is going downwards, so that's the way that we're working this, whereas I resolved it upwards, so this A is upwards, so our actual acceleration will be minus 6.44 when we put it into the equation. So we've got 0.8 equals nothing because V is nothing, minus 0.5 times minus 6.44 times t squared, t being what we want to find out. So that's 0.8 equals 3.22 t squared. So t squared equals 0.8 divided by 3.22. So if we put that in and square root it, we'll find that t equals 0.5 seconds to the nearest 1 decimal place.